Okay, so you use this thing every single day, right? And you probably don't even think about it. That little search bar, the one that seems to just know what you're thinking. Well, the engineering behind that is, honestly, it's a masterclass in speed and scale. So let's break down how it actually works. I mean, we've all been there, haven't we? You start typing a few letters and boom, the exact thing you were about to search for just pops up. It feels like some kind of mind-reading trick, but it's not magic. It's an incredibly high-performance system, and it's working in real time to guess your next move. The real question is, how on earth does it pull that off? So the first thing you have to understand, and this is the most important part, is the need for speed. The whole experience just completely falls apart if it doesn't feel instant. And that window it has to respond in, it's almost impossibly small. 100 milliseconds. That is the magic number. You know, research from places like Facebook has shown that if a response takes any longer than that, our brains perceive it as clunky or even broken. So the entire system, the whole thing, has to find suggestions, sort them, and send them back to you literally faster than you can blink. It's wild. And here's the kicker. It has to maintain that incredible speed while operating at a massive global scale. Just think about it for a second. Every single letter you type fires off a new request to the server. Now multiply that by millions of people all typing at the exact same time. At its busiest, a system like this is dealing with something like 48,000 queries every single second. That is just a staggering amount of traffic. And remember, every single one of those 48,000 requests needs an answer in under 100 milliseconds. The scale is just mind-boggling. Okay, so if you're an engineer and you're faced with this insane challenge of speed and scale, where do you even start? Well, the answer is usually you start with the simplest, most obvious idea that could possibly work. And that first idea, the most straightforward one, is to just use a standard database, right? You just create a massive list of every search query ever made and dump it in there. Then every time a user types a letter, you just ask the database, hey, can you find all the searches that start with, say, TW, and then sort them by which ones are most popular? Seems simple enough. And this is where that simple idea just completely breaks down. Look, if you only have a few thousand search terms, it works okay. But when you're dealing with billions of past searches, trying to run that kind of find and sort query for 48,000 people every second, well, you create a huge bottleneck. It's just painfully slow. There's no way it's going to hit that 100 millisecond target. So to get around this speed problem, we have to ditch the standard database idea. We need a totally different tool for the job. We need a data structure that is built from the ground up for this one specific task, matching the beginning of words or prefixes. And so let's meet the hero of our story. It's called a tree, which you might also hear called a prefix tree. It is an incredibly clever data structure where basically the paths you take from the top, the root, down through all the branches actually spell out words and phrases. Now, the real genius of the tree is how it saves so much space. Let's say we've already added the word tree. When we go to add the word try, we don't start all over again. The system is smart. It reuses the T and the R nodes that are already there, and it just branches off to add a Y. It makes it super efficient for storing tons of words that start the same way. Okay, but finding the words that match isn't the whole story, right? We need to know which ones are the most popular. So we add another piece of information. On any node that represents the end of a word, like that final E in tree, we also store a little counter that keeps track of how many times that specific word has been searched for. So at this point, the try is looking like the perfect solution, isn't it? It's great at finding prefixes, but there's a hidden trap, a performance issue, that could still make the whole thing way too slow. Okay, just imagine this. A user types the letter T. The system can instantly find that T node in the try. No problem. But then what? To find all the possible suggestions, it would have to crawl through every single branch that comes after that T node. We're talking potentially millions of words. And then it has to sort all of them by popularity. There is just no way to do all that work in less than 100 milliseconds. And this is the big aha moment. This is the secret sauce for the entire system. The idea is, what if we don't calculate the top results in real time when the user is typing? What if we do all that hard work ahead of time? So here's the trick. When the try is being built, way before you ever type anything, the system pre-calculates the top 5 or top 10 suggestions for every single node in the entire tree. It then just stores that little list right on the node. So when you type TR, the system just zips over to that R node, grabs the pre-made list that's already sitting there, and sends it right back to you. There's no searching, no sorting on the fly. It's practically instant. It's a classic engineering trade-off, right? You use a little more memory to store these lists, but in return, you get a massive, massive boost in speed. All right, so we have this really clever, super optimized data structure. Now let's zoom out and look at the final part. How do we fit this into a full system? One that's robust enough to handle billions of queries from all over the world.
First things first, you can't be updating this gigantic trie every single time someone searches for something. That would just be way too slow and use up a ton of resources. Besides, the most popular suggestions, they don't really change minute to minute anyway.
So instead, there's this whole other system working completely separately, behind the scenes. Think of it like a data factory. It starts by collecting the raw logs of every search. Then, on a regular schedule, maybe once a week, these aggregator machines chew through that mountain of data to count up how frequent every search term is. After that, a bunch of worker servers take that data and build the brand new massive optimized tree with all those pre-cached top results we talked about. And only when that new tree is 100% ready to go is it loaded into the live system for you and me to use. And that separation is absolutely critical. When you type into the search bar, your request never goes anywhere near a slow database or that complicated factory pipeline. Nope. It goes directly to a server that has that finished tree loaded right into its super fast memory. That's the key. That's what makes it possible to get those pre-calculated results back instantly. But what happens when the tree gets so big it doesn't even fit on one server anymore? Well, you have to split it up or shard it across a bunch of different machines. Now, you can't just do a simple split, like putting A through M on one server and M through Z on another. That would create hotspots because way more searches start with the letter S than, X. So the really smart way to do it is with something called a shard map manager. You can think of it like an intelligent traffic cop. It looks at all the past search data and figures out how to slice up the tree into perfectly balanced pieces, making sure no single server ever gets overwhelmed. So, to wrap this up, when you see that autocomplete suggestion pop up, don't just think of it as one simple trick. It's really a whole system of clever engineering ideas all layered on top of each other. It starts with those crazy requirements for speed and scale. That forces you to use the right tool for the job, the trie. Then comes that game-changing optimization, pre-caching the top results at every step. And the whole thing is supported by that powerful offline data factory that gets everything ready for that instant blink-of-an-eye response.
It's kind of wild when you think about it, right? Now that you know how it works, that little autocomplete box is more than just clever code. It's almost like a real-time snapshot of our collective consciousness, what millions of people are thinking about right now. All of that curiosity, gathered up, sorted, and sent right back to us, in less time than it takes to blink.